Now let's take a second and review what happens when we look at derivatives of these power series. So I'm going to start by looking at term by term and then sort of generalize that into some pattern. So if I have f of x defined as a power series and I start to take the derivative, what's going to happen to that very first term? That very first term is going to be go to 0. So this c naught, so this guy right here is going to 0 out. And the c1x, the derivative of it's going to be c1. So in expanded form, I'm going to have c1 plus 2c2x plus 3c3x squared plus dot dot dot. So in general, right, essentially our pattern starts at n equals 1, not n equals 0, where the original one did. And we can expand that out infinitely if we wanted. But the coefficient is a function of the exponent. So the n times n x minus to the n to the x minus 1 power. In short, that c sub n term, this term, is just some arbitrary constant that was in the original pattern. Okay. Then we jump to the second derivative. So the second derivative, the derivative of c1 is going to be 0, and then I'm going to be left with 2c2, and then I'll pull down the 2, so 3 times 2, c3x plus dot dot dot. And yes, I know, 3 times 2 is 6, but I'm purposely writing it like that. So when we generalize this, we can recognize that, okay, yeah, that is the pattern going on there. So in this case, the general term for the second derivative wouldn't start at n equals 1, it would start at n equals 2. Of course, we can expand that out. Then we have our constant term. And then what happened to our exponents, it was n times n minus 1. X to the n minus 2 power, and then we just expand that out. Okay, so the identity property says if a power series is equal to 0, the only way that would be relevant is if the constant itself happens to be 0 itself. So that's just sort of the identity property, and that's similar to the identity property of kind of like identity property multiplication, where the only way if I'm multiplying two things I get 0 is if one of the terms itself has to be 0. And then we define another vocab word, so analytic at a point. Function is said to be analytic at a point if it can be represented. Oop, that is slightly off the screen there. If it can be represented by a power series in x minus a with either a positive or infinite radius of conversion. And the two classic examples of this would be the Taylor series and the Mclaren series. So the Taylor series is a power series centered around a, whereas the Mclaren series is centered around 0. It does not mean it equals 0, it's just f of 0, f prime of 0, as opposed to f of a, f prime of a, etc. And if you remember from your Cal 2 days, there were some interesting patterns that we could do with this. And as stated, here's a reminder of some of the Mclaren series that we've encountered in the past. So if we recognize the power series patterns, then we can identify the specific function themselves, and then we have associated intervals of convergence with those different power series. Okay, so if we were asked to find the power series of a product of two functions, then we would expand what we know about e to the x and sine of x, look for interesting patterns, simplify the best we can. So if I break that up, so the e of x pattern, looking back at our lovely chart there, was 1 plus x squared over 2 plus x cubed over 6 plus x to the 4th over 24 plus dot dot dot. And then the sign of x pattern was x minus x cubed over 6 plus x to the 5th over 120 minus x to the 7th over 5040 plus dot dot dot. Okay, so if I think about this as a series of essentially multiply the term by terms together. So the way we're going to tackle this is we're going to kind of, okay, so we're going to start with 1. And I'm going to take 1 times the entire pattern there. Now, I'm only going to expand it out so many terms because I'm trying to recognize, I'm trying to figure out what's going to happen with each additional term in this pattern. So I only need to do this enough long ways until I recognize what the general pattern is. So if I multiply by 1, I would get x minus x cubed over 6 plus x to the 5th over 120 minus x to the 7th over 5040 plus dot dot dot. Okay, so that's just for the x term. I'm sorry, for the 1 times that expansion of sign. So if I come in and I do it with the x, that's going to give me x times x, which is x squared, x times minus x cubed over 6 is going to give me minus x to the 4th over 6. That's going to give me plus x to the 6th over 120 minus x to the 8th. Sorry, my voice is going away. Over 5040 plus dot dot dot. And then let's do one more term and then see if we can recognize some patterns here. So if I take x squared over 2, right, that is going to give me, and I'm going to carry this down in this little empty space here. Just want to make sure I don't run out of room. All right, so that's going to give me x cubed over 2 minus x to the 5th over 6 plus, sorry, my denominators are not quite right. X cubed over 12, because it's 2 times 6. And then x to the 5th, which is the, hold on. I had it right the first time. That one was 2. This is the 12. So the 6 is not the 6, it's the 12. X squared times x to the 5th over 120 would be x to the 7th over 240. And I think I'm just going to do the magic dot 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 at that point, because I think I have enough evidence that I can see a general pattern emerging from this to some degree. But I could, obviously I could keep expanding this thing as much as I wanted. Okay, so then I'm going to collect up things that would add together, so like terms. And I see for the first one I have an x, and I only see one x squared in this entire expansion. So there's a single x squared there. X cubed, I see 2 things with it. So I see an x cubed over 6, so negative 1/6 plus, and then I see another x cubed with 1/2. And I'm not going to find any other x cubes in this expansion. And then x to the 4th, let's see, I see a negative 1/6 there, and do I see anything else? Okay, and I do want to point out that there was one spot I did not expand to fully catch this. So if I did this x cubed times that x right there, that would also give me an x to the 4th term, which would give me plus 1/6. So plus 1/6 x to the 4th. Let's see how many x to the 5ths I have. So x to the 5th, I have 120. What else? I have a minus 1/12. And is there any other thing that maybe I did not consider when I was distributing there? And yeah, I've got another spot. So I'm going to come in here and I'm going to say if I took this guy, x to the 4th over 24 times x, that would have also given me an x to the 5th. So that would give me 1 over 24. X to the 5th plus dot dot dot. Okay, so again, as you remember from your days with these power series expansions, your accuracy is only determined by your ability to expand this as far as required. Anyway, so at this point then, we would just simplify all of our fractions. So that would give me x plus x squared plus x cubed over 3. X to the 4th cancels out. That'd be minus x to the 5th over 30 plus dot dot dot. So that would be our power series expansion of e to the x sine x.